Alright, hey everybody, this is video 713. It's our third video working on our standard about graphing rational functions, and we're going to be looking at how to gather some information. If you've got your graphing calculators and you like to reference the picture of the graph, I'm going to have a bunch of different equations, so if you want to look at the picture and compare it to the information that we get, that might be a good idea. So it's up to you, and you'll need to pause then and enter it before you go ahead and proceed with me, but it might be a good idea to reference an image along with the information. Here we go. So we're going to find some information starting with our vertical asymptotes and our x-intercepts. They both have a very similar strategy, but what I want to stress is that there's two ways to do this. You can memorize a bunch of steps to take and understand that you follow these procedures, and if you follow the procedures you get to the answer. Another way to do this is to really understand why you're following these procedures. Because if you understand why you're following the procedures actually just will happen naturally. And let me explain. Vertical asymptotes occur. We will find vertical asymptotes where the function is undefined. So if you know where a function is undefined, then you know where to find vertical asymptotes. So if you make the connection between an undefined, a place where the function will be undefined and the vertical asymptotes, you know exactly what to do. A function is undefined when the denominator is 0. So if you ask yourself, where will the denominator be 0, you've also answered the question about where your vertical asymptotes are. So make the connection between these two, and you've answered two questions in one. This function is undefined when the denominator is 0. So that happens when the denominator is 0. So how do you find them? You set the denominator equal to 0. That is x plus 4 equals 0, and we find that our vertical asymptote is located at x equals negative 4. Alright, let's go to the next function. Same thing. I want to know where are my vertical asymptotes. I could be asking you the same question, where is this function undefined? If you know that those two go together, it's the same answer. So that means I have to set the denominator equal to 0 because that's where the function is undefined. So x squared minus 3x minus 4 is equal to 0. This one does require me to factor. So I get x minus 4 and x plus 1. So that means x equals 4 and x equals negative 1. And those are my vertical asymptotes. They're also the same places where this function is undefined. That's actually the cause of the asymptote. Alright, the next one we're going to look at are the x-intercepts. My x-intercepts are when y equals 0. Well, how come? Well, x-intercepts occur when the height of the function is 0. So when it crosses the x-axis, that means y is 0. Well, how can I do that? That means I have to set it equal to 0. In other words, make this equal 0. So the question I ask you is, well, when is a fraction equal to 0? When does the entire fraction have the value? I'm going to write the question down. When does a fraction, an entire fraction, have the value 0? And the answer to that is when the numerator is 0. Think about slope. The slope is 0 when the numerator is 0. So it doesn't matter what's on the bottom. If we're looking at when does a fraction equal 0, it's when the numerator is 0. Well, if I want the fraction to be 0 because I'm trying to find the x-intercepts, then I will set it equal to 0. So my x-intercept is at 3, 0. Now notice my vertical asymptote is written as an equation of a vertical line, but my intercept is written as an ordered pair. There's a big deal being made here. If you just tell me your vertical asymptote is negative 4 and your intercept is at 3, I don't know which is which. So writing them in the correct form, the correct communication is very important. Let's take a look at the second one. So here I'm looking for, when does the fraction have the value 0? That means the numerator has to be equal to 0. So I will take my numerator and I will set my numerator equal to 0. Don't multiply it out. This is ready for me to use a zero product property. So x equals 6 and x equals -2. Those right now are in the form of vertical lines, and intercepts aren't vertical lines, they're ordered pairs. So 6, 0 and -2, 0. Those are my x-intercepts. All right, moving on to y-intercepts. Y-intercepts occur when x equals 0. This one, actually, the procedure is much more simple. If x equals 0, I just substitute in 0. So I'm going to go ahead and do that. If I substitute in 0, I get 0 minus 9 over 0 plus 3, which is -9 over 3, which is -3. Once again, I want to write this as an ordered pair because it is a location on the graph that is a single spot. Okay, so it's 0 equals 0, -3. Let's do the next one. Substituting in 0 to find my y-intercept. This simplifies to -2 times -3 over -4, which is 6 over -4 or -3 halves. Once again, it's written as an ordered pair because it is a location on the graph. 0, -3 halves. For y-intercepts, you will only ever have one y-intercept, and that is because if I had two y-intercepts, then this would not be a function. So you will only have one. Write it down that you will only have one y-intercept. Alright, so the next type of asymptote we're going to talk about is the horizontal asymptote. That is that we're looking at horizontal lines. Okay, let m be the degree of the numerator. That is that it is the largest exponent of the numerator, and n be the degree, as in the largest exponent of the denominator. For example, if I have a function where I have x squared plus 3x minus 2 over x to the fourth plus 7x, I look at the highest exponent of each. So the degree of the numerator is 2 and the degree of the denominator is 4. So as long as you're looking at the powers, the m and n don't matter as much. Just look at the power. Alright, so in the first situation, we've got three different cases here. Okay, so you'd have to analyze this to make a decision about your horizontal asymptotes. The vertical asymptotes we went through naturally, the x and y intercepts also naturally, but the horizontal asymptotes take us to analyze. When it is bottom heavy, that is, that the degree in the bottom is bigger, or the degree in the top is smaller. So you have the smaller over the larger degree. And it only matters about the degree. Forget what numbers are associated, just look at the exponents. If it is bottom heavy, then we have y equals 0, which is the x-axis, as our horizontal asymptote. Okay, for example, you'll see this type of graph be that it's not crossing the x-axis here. So we see that right there. That is a horizontal asymptote of y equals 0. And that is that the degree in the bottom is larger than the degree in the top. When they have the same degree, that is that we have an x squared over an x squared, or an x cubed over an x cubed. Or simply, if we have something like this, f of x equals 2x plus 7 over 3x plus 4. These have the same degree. Then what we get is the ratio of the lead coefficients. So in this case, my horizontal asymptote would be y equals 2/3. That is the horizontal line that is our asymptote if we have the same degree. The last one is, what if it is top heavy, as in the degree in the numerator is bigger? I could have an x cubed plus 3x minus 1 over just an x squared plus 6x, for example. Okay, my degree is bigger in the numerator. This will lead to no horizontal asymptotes. Okay. Alright, so you make a decision based on the exponent and comparing them to each other. Last slide coming up. Oblique asymptotes. These are very unique and they only occur in certain situations. And that is when the degree of the numerator is exactly one more than the degree of the denominator. So this only works if you have something like an x squared over an x, or an x cubed over an x squared, or an x to the fourth over an x to the third. It only occurs in these situations. Okay? And what happens is you get a slant asymptote or an oblique asymptote, and this is in the form of y equals mx plus b. And here is how we find it. First, we identify that there's going to be an oblique asymptote. Then we're going to use something, and I'll get more into this in the next unit because you're going to use it only for this situation in this unit. And that is something called synthetic division. Synthetic is fake, but we're going to use it for this case, synthetic division. And you're going to take the opposite of this number, and then you're going to only write the coefficients. So I write 1, -3, and 7. And you're going to follow two steps. The first step is to bring the 1 down from this case, and then you're going to multiply these two together, and then add these two together. This leaves you with two numbers on the bottom. Don't even worry about that last piece. This leaves you with two numbers on the bottom, and that becomes your slope and y-intercept. So y equals 1x minus 4 is your oblique asymptote. We're going to try it again, and we can definitely try some together. You're going to take the opposite of this number. You're going to take the coefficients, that's 1 and 5 and -2. You're going to drop down the first number. You're going to multiply and add. This becomes the y equals 1x plus 8. That is the equation of your slant asymptote. We can definitely practice some more synthetic division along with all of the other things that we've talked about in this video.